Okay, so the last talk of today is going to be by Ana Queda, from IMPA, and she's going to talk about the Kawamata-Morrison conjecture for quotients of Abelian varieties.
This is a joint work with another PhD student, Martina Monti. She's based in Poitiers and Milano. I will start introducing what is an F divisor. A divisor is said F if its intersection with every curve on a variety is non-negative. And we can consider this vector space here. There is the neuron severity tensored by R, or in an equivalent way, divisors tensored by R, modulo numerical equivalence. And if we consider the F divisors inside this vector space, they form a convex cone. We can also consider another cone that will be interesting for us is the NF effective cone. Is the NF cone intersected by effective divisors that also form a convex cone. And so these convex cones are interesting because they say a lot of things about our projective varieties. For example, we can understand fiber space structures or contractions of our varieties by studying these cones. And then we can translate our problem from a projective variety perspective to a convex geometry perspective, which gives us a lot of different tools to deal with this. Moreover, the shape of the NF cone depends a lot on the canonical divisor of our variety. For example, when our variety is Fano, the NF cone is rational polyhedral. What this means? This means that it has like this nice shape here with a finite number of faces. And in this case, each one of these faces can be associated to a fiber space structure or to a contraction of our variety. But today, I'm not interested on Fano. I'm interested on varieties that have numerically trivial canonical divisor. But before, let's talk about how the cone conjecture appeared. So the cone conjecture was first proposed by Morrison in his papers Compactifications of Moduli Spaces Inspired by Mirror Symmetry and Beyond the Kähler Cone. And there, it was first proposed as a conjecture for certain kinds of Calabi-Yau varieties. And on the case that conjecture holds, it guaranteed the existence of a compactification over certain parameter spaces. And basically what happened, by now, when Morrison proposed this conjecture, it was already knew that K3 properties had the property of the conjecture. And he realized that because it had this property, existed a compactification of a certain parameter space. But then, another person saw the conjecture proposed by Morrison. Morrison first proposed it to the Kähler cone and modified it a bit. It was Kawamata. Kawamata was someone that was, Carolina mentioned him on her lecture before today. He was someone that was really interested in birational geometry and minimal model program. And he was the one that realized that this conjecture would have some nice implications when studying birational geometry. And so I will now talk very briefly, start talking about the trivial canonical divisor case. Actually, I will give an example. So for Abelian surfaces, I said before that for how our NF cone looked like when we were talking about Fano varieties. But for Abelian surface here, we have that our cone is on this shape, is round. So in this case, we don't have a finite number of faces. And so how can we relate the contractions of our varieties or fiber space structures with this cone? So in this case, what we have is that I will denote by A the space of contractions or fiber space structures associated to a face, two faces of the NF effective cone. And in this case, we have that A is not finite. But there is an equivalence relation that we can put on A such that this is finite. And what is this equivalence relation? Is this one. So I given two elements in A. We have that. Sorry, okay. Maybe here, like. So. So in this case, I is not finite, but if we consider this equivalence relation given by the automorphisms of the variety, then this set is finite. So what I want to say is that although we don't have a finite number of contractions or fiber space structures, I can choose a finite number of them, and with the automorphism group of my variety, recover all the finite, all the contractions or fiber space structures, just by acting the automorphism group on this finite number that I chose. Or the same thing, more generally, the same thing can be said about faces of the NF effective cone and using a similar equivalence relationship. So I don't have a finite number of faces, but if I use this equivalence relation, then I can have a finite number of faces unless something like that. And another way of saying that is exactly the cone conjecture, the way that it was proposed by Kawamata. This means that I have a rational polyhedral domain for the action of the automorphism group on the NF effective cone, meaning that I have a finite number of faces. I have a rational polyhedral cone inside the NF cone, such that this cone, with this cone and the automorphism group, I recover all my NF effective cone. And moreover, if I consider the interior of this rational polyhedral cone that I'm saying, with acting with phi in the same cone, this is empty unless the pullback is the identity on N1, on the N1 of my variety. And so I will try to now say what is known of the cone conjecture right now. And so I will recall you classifications of complex surfaces with trivial canonical divisor, with numerically trivial canonical divisor. So we have K3 surfaces, Abelian surfaces, Enrique surfaces, and hyperelliptic surfaces. And the case for surfaces is for surfaces, the conjecture is completely solved. So the K3 surface case was proven before the conjecture was stated, was one of the motivating cases, was done due Sturck. And the hyperelliptic, Enriquez, and Abelian were done by Kawamata on the paper where he established his version of the conjecture. I recall you that Enriquez surface is finitely tightly covered by a K3 surface, and a hyperelliptic surface is finitely tightly covered by an Abelian surface. So what I'm saying is, so what can we say about higher dimensions? How we approach this conjecture? So I also recall you another theorem that is called the Bovide-Bogolov decomposition. There is, sorry. I consider M a smooth projective variety with a numerically trivial canonical divisor again. And when this happens, this variety is covered by, finitely covered by a product of an Abelian Calabi-Yau manifolds and irreducible symplectic manifolds. And so we know by now that for what we know, what is known of the conjecture for these cases. So for Abelian varieties case, was already proven by Prendergast-Smith. IHS manifolds were proven by American and Verbitsky. And Enriquez manifolds for some prime covers were done by Pacienza and Salti. And what can we say when our finite tile cover is, when our surface is covered by an Abelian variety? So in this case, we say that Y, our surface, is called a generalized hyperelliptic variety. And in fact, this is the quotients that I mentioned on the title of my lecture. So in these cases, these varieties can be written as a quotient of an Abelian variety by a subgroup of the automorphism group that is finite and acts freely on X and without any translations. So now I will try to give you a bit of the strategy to solve the problem. And so the first thing is we consider a convex cone on a vector space V. And I will call the automorphism group of the cone as the linear transformations of V that preserve the cone. And I define the rational whole by this C plus here. And this is the convex whole of the closure of C intersected with VQ. VQ is a key structure of this vector space V. And so there is this theorem due to Ash of convex geometry that says that when we have a homogeneous self-dual cone and arithmetic group on the connected component of the identity of the automorphism group of the cone, we know that there is a rational polyhedral fundamental domain for the action of gamma on the rational whole. And so basically, this is basically what we want in some sense. So I will just write this here on the board just for us to keep in mind this strategy. And so so I have my theorem that says that C homogeneous self-dual cone. I will define what is a homogeneous dual cone in a couple of minutes. And arithmetic then I have that there is a rational polyhedral fundamental domain for gamma acting on the rational whole. And so, in our case, also we have that for a GHV, what me and Martina have done was basically adjust what Prendergast-Smith did for the abelian varieties case. And what we could do that is because our ample cone and our automorphism group can be written in terms of the ample cone and the automorphism group of the original variety, in the sense that the ample cone of Y is the ample cone of the fixed elements, the elements that are fixed by G on the original ample cone, and the automorphism group is the normalizer of the automorphism group quotient by G. And so, for us, our C will be ample Y that is equal ample G. Our C plus is NF, and in fact, this is the NF effective already. And our gamma is this guy. But we can improve a little more. So if we know also that if there is a rational polyhedral fundamental domain for a subgroup of the normalizer here, it will also exist for the normalizer. So here we can change our gamma. Not instead of considering the normalizer, we can consider the centralizer. So basically what I'm saying is that we can reduce our proof in 2 steps. The first one is to prove that my ample cone now is an homogeneous self-dual cone. And the second one is to prove that my centralizer is arithmetic in the connected component of the identity of the automorphism group of the cone. And okay, and so, okay, what are homogeneous self-dual cones? So these are 2 definitions, but instead of really giving the definitions, I will maybe tell you something that is better. I will tell you how they look like. So there is a theorem due to Weinberg that classifies all indecomposable homogeneous self-dual cone. So what I'm saying that any homogeneous self-dual cone has to be a direct sum of these 5 cases here. The first 3 cases is the one that is going to be the one that are going to be interesting to us. So they are basically positive definite matrices under symmetric matrices over R, C, and the of the Hermitians. The fourth one is the spherical cone, and the fifth one is the 27-dimensional cone of positive definite 3 octionic Hermitian matrices. So our idea now to keep in mind is that we want to write our ample cone as a sum of the first 3 of them. And how we're going to do that? So I will recall you before some things about abelian varieties. So an automorphism of an abelian variety can be written as a composition of a translation and an endomorphism, an invertible endomorphism of the abelian variety. An endomorphism of the abelian variety is a holomorphic map that preserves the group structure. And we have some tricks about abelian varieties, is that we can get a group homomorphism in this way, that goes fixing an element of the Picard group. We can have this phi d that goes to x, to its dual, that take an element x to the pullback of the translation tensored by d minus 1. And using this definition, we can define an involution on my endomorphism algebra on the set over Q. So in this way. And why this involution is nice? Because this is through using this involution and fixing an ample line bundle F, L, we can really embed our N1 in this in the endomorphism group of the abelian tensored by R. So this endomorphism group, this algebra of endomorphisms of my abelian variety has a representation. Somehow is we are dealing with matrices. So what we are doing is embed my N1 in a group of matrices. That's what we are going to do. That's what we want. And actually, so we define the embedding in the way that it's written, like I take D to phi L minus 1 to phi D. And this F has established the following bijections. So my N1 here are exactly the elements that are preserved by the Rosati involutions. And my ample cone are the elements that are preserved by the Rosati involution, whose characteristic polynomial has only positive roots. And so we have results of classifications of algebra with involutions that we can associate this pair, endomorphism algebra of abelian tensor by R, Rosati involutions, to this product of matrices. So, and where the Rosati involution is sent to a positive definite involution given by the conjugate transpose on each factor. And the same thing, so I recall you that we want to do this case, the case that the ample for ample x fixed by G. And the same thing is true when we consider this. And so, as a consequence, we have these things. So first, who are the N1G? Are the elements that are preserved by the Rosati involution inside here. And who are the elements that are preserved by the conjugates transpose on each factor? Are the symmetric matrices. The second one is the same thing. So the elements that are preserved by who has this property of the characteristic polynomial has only positive roots are exactly the positive definite matrices. So we establish this correspondence. And so, but moreover, how can we are interested on the action of the pole of the automorphism group on the N1. And so how can we do that? So how can we do that looking for the endomorphism algebra? So there is something like an alpha that makes this diagram commute. And in fact, yes, And also, it also involves the Rosati evolution on its definition. So I take an element L to phi prime, composition to L phi. And basically, the last part, I will try to say quickly, is it involves what I want is that, so the first thing I'm going to do is, define what is an arithmetic group. So the idea of arithmetic group is that if I have an algebraic linear group, so a group of matrix with complex entries defined over Q, I can define this GZ as the matrix with integer entries. And so a group is arithmetic if it has more or less the same size of this GZ, meaning more precisely that is commensurable with GZ. So the intersection of GZ in this group is of finite index in both GZ and gamma. And so, as I said, the idea is that GZ corresponds to the matrices in G with Z entries. And what we want is that this guy is a arithmetic group in the connected component of the automorphism group. And for the Abelian case, we know that this is arithmetic here. So what we want to do now is basically from the Abelian case, I think maybe this is easy to accept, but it was very easy to realize that this was also true. So basically, in the proof of the Abelian case, we know that this is true if we don't consider elements that are G invariants. And so, in our case, it's using the same path, the same reasoning, we also know that this is true when we consider the G invariants. And so, how it connects with the centralizer? So, we can choose an ample-line bundle that is G invariant to define our Rosati involution, and then we obtain that taking the Rosati involution is the same as taking the inverse element. And when we do that, by definition, our centralizer is exactly the elements that are invertible, the invertible elements here, and that are fixed by G. And using the same idea for the Abelian cases, we are able to prove that this is arithmetic on the automorphism group. And thank you. This is all.
Thank you, Anna. Any question, comment?
Is there anything here that's obviously incorrect in characteristic P?
Sorry?
Is there anything that goes wrong, obviously, in characteristic P for this kind of question?
Incorrect. I don't really know, nothing about characteristic P.
Is there anything particular you can say in the case where X has complex multiplication?
Has what?
Complex multiplication.
I'm not sure, honestly.
Okay. Because it's look like you can say more in the case where, in that case, with your techniques.
Okay.
If there are no more questions, let's thank Anna again. And we meet again tomorrow.